The Andromeda Galaxy has played a crucial role in reshaping our understanding of the universe and where we fit within it. Take our galaxy, the Milky Way, for example. It's just one among approximately 100 billion galaxies visible to us. Andromeda's presence provides compelling evidence that the universe and its creation don't center around Earth. This discovery shattered the old belief that the Milky Way stood alone, revealing that we're merely a small piece of a vast cosmic puzzle. Our knowledge about Andromeda has grown significantly over the past century, mainly from observations made right here on Earth. But with advanced tools like the James Webb Space Telescope, our view has changed dramatically. Recent data from the JWST has challenged what we thought we knew about Andromeda, leaving scientists amazed. This unexpected twist has led to a new mystery, the JWST picking up signals from our neighboring galaxy, Andromeda. It's a discovery that has captivated the scientific community. This new understanding has also shifted our perception of the Milky Way throughout history. In the past, with limited technology, it appeared as a faint band of light across the night sky, sparking various interpretations and myths. But with each advancement, our view of the cosmos evolves, reminding us of our ever-changing place in the universe. Throughout history, the Milky Way held a mystical and central role in the beliefs of various cultures. However, as our scientific understanding advanced, particularly with the advent of telescopes and the pioneering work of astronomers like Galileo Galilei, we came to grasp that the Milky Way wasn't merely a celestial idea, but rather a vast assemblage of stars, planets, and celestial bodies. This realization completely transformed our perception of where we stand in the cosmos. Today, thanks to modern telescopes and ongoing astronomical research, we now have a much clearer understanding of the Milky Way as a barred spiral galaxy teeming with billions of stars, including our own Sun. In the 1920s, Edwin Hubble, an American astronomer, made a groundbreaking discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble's observations of distant nebulae beyond the Milky Way revealed a profound truth. They weren't part of our galaxy, but separate galaxies in their own right, each hosting billions of stars. Among these galaxies was the Andromeda Galaxy, also known as M31, one of the nearest to our own. The Andromeda Galaxy has a fascinating history of observations stretching back for centuries. One of the earliest documented instances of this cosmic marvel dates back to the 10th century, when the Persian astronomer Abdul al-Rahman al-Sufi depicted it as a small cloud on star charts from that era. What's remarkable about al-Sufi's observations is that he identified this distant celestial entity without the aid of telescopic instruments, relying solely on his sharp eyesight and astute observations. It wasn't until 1612 that a detailed portrayal of the Andromeda Galaxy, based on telescopic observations, was presented by Simon Marius. His contributions laid a solid groundwork for future astronomers to delve into the study of this immense cosmic structure. Later, in 1764, the esteemed French astronomer Charles Messier included the Andromeda Galaxy as M31 in his renowned Messier catalogue, albeit mistakenly crediting its discovery to Simon Marius. Nevertheless, this oversight doesn't diminish Messier's pivotal role in bringing Andromeda to the forefront of astronomical knowledge. For nearly a century following these initial observations, astronomers around the globe diligently sought to unravel the mysteries of this enigmatic galaxy, each contributing to the collective understanding. Before this flurry of inquiry, Galileo Galilei, an Italian astronomer, reshaped our comprehension of the Milky Way during the early 17th century. Armed with his pioneering telescope, he made revolutionary observations that challenged the prevailing cosmological beliefs of the time. In 1750, English astronomer Thomas Wright put forth a groundbreaking hypothesis in his work titled An Original Theory or New Hypothesis of the Universe. According to Wright's conjecture, the Milky Way wasn't a haphazard scattering of stars in space, but rather a flat layer comprised entirely of stars. He also proposed that a segment of this expansive structure encompassed our own solar system. Although Wright's hypothesis represented progress in comprehending the Milky Way's structure, it remained constrained by the technological limitations of the era. A significant breakthrough in understanding the Andromeda Galaxy occurred in 1864, credited to the English astronomer William Huggins. Through his pioneering observation, Huggins analysed the spectrum of Andromeda, discerning its divergence from that of a typical gaseous nebula. This pivotal insight paved the way for a more accurate understanding of Andromeda's true nature. With an estimated mass between 1 and 2 trillion times that of our Sun, the Andromeda Galaxy emerges as a colossal cosmic entity situated relatively close to us in the expansive realm of space. Based on accumulated research, scientists ascertain Andromeda's age to be approximately 10 billion years, marking it as an ancient presence within the cosmic timeline. An intriguing aspect of Andromeda's formation revolves around the notion that it originated from the merging of numerous smaller proto-galaxies. This hypothesis suggests a gradual amalgamation of smaller galactic components over billions of years under the influence of gravity, culminating in the grandeur of the Andromeda Galaxy we behold today. Such galactic mergers are commonplace in the cosmos, actively shaping the development and structure of galaxies. Yet, for an extended period, astronomers held the belief that Andromeda surpassed our own Milky Way galaxy significantly in mass. This misconception is understandable given the limitations of observational tools during the 1700s and 1800s. However, recent research has prompted a reassessment of these assumptions. Fresh insights have led scientists to revise their estimations of Andromeda's mass downward while simultaneously elevating the mass attributed to our Milky Way. Presently, it's understood that the masses of these two cosmic titans are much closer than previously believed. In essence, if one was situated on Andromeda and peered towards Earth, they would perceive a galaxy of comparable magnitude. This realization underscores the immense scale of the Milky Way itself. Astronomers unanimously agree on the physical dimensions of the Andromeda Galaxy, which stands out for its vast expanse. With an impressive diameter of about 220,000 light-years, Andromeda extends further than our own Milky Way. This substantial size dwarfs the estimated diameter of the Milky Way, which ranges from roughly 100,000 to 175,000 light-years. Consequently, Andromeda emerges as a truly significant cosmic presence, dominating a considerable swath of space. This updated perspective also underscores the intricacies and hurdles involved in precisely measuring the mass of galaxies. Deep within the Andromeda Galaxy lies a supermassive black hole, exerting an immensely strong gravitational pull on the stars surrounding it. As these stars orbit the black hole, they trace elliptical paths akin to the planets orbiting the Sun within our solar system. At a specific juncture in their elliptical orbits known as the perihelion, stars draw closest to the black hole, experiencing the most intense gravitational forces. This gravitational tug propels the stars to their highest speeds, causing them to bunch up and become more densely concentrated around the black hole. In this process of clustering, stars emit energy in the form of radiation, including visible light and various other types of electromagnetic radiation. The intensified clustering of stars and the subsequent emission of radiation contribute to the heightened luminosity observed at the core of Andromeda's active galactic nucleus, AGN. We'll delve deeper into this concept shortly. This unique characteristic offers valuable insights into the gravitational dynamics and interactions between the supermassive black hole and the surrounding stellar bodies. To gain a better understanding, let's explore what an AGN entails. An active galactic nucleus, commonly referred to as AGN, constitutes a vigorously energetic domain situated at the heart of a galaxy. It exhibits intense emissions spanning various wavelengths, ranging from radio waves to X-rays. The energy output of AGN stems from the presence of a supermassive black hole nestled within the galaxy's core. These supermassive black holes epitomize extraordinarily dense regions in space, where an immense concentration of mass occupies a remarkably compact volume. When astronomers utilize advanced telescopes like the Hubble Space Telescope to observe the active galactic nucleus, they encounter a fascinating phenomenon. One of the most captivating aspects of the Andromeda galaxy is its active galactic nucleus, AGN. This nucleus exhibits two distinct points of concentration, indicating regions where light and other forms of radiation emanate with greater intensity compared to their surroundings. The more luminous focus is positioned slightly off the true galactic center, housing the supermassive black hole. Estimated to weigh between 1.1 to 2.3 multiplied by 10 to the power of 8 solar masses, this black hole's mass translates to approximately 110 to 230 million times that of our Sun. Supermassive black holes are commonly found at the cores of galaxies, including our Milky Way, where they wield significant influence over galactic evolution and dynamics. When material such as gas and stars ventures too close to a supermassive black hole, it coalesces into an accretion disk around the black hole. This swirling disk of material undergoes heating, emitting intense radiation across various wavelengths, thereby contributing to the luminosity of the AGN. Upon scrutinizing the active galactic nucleus of the Andromeda galaxy, astronomers discern a heightened concentration of brightness near the central supermassive black hole. This distinctive feature arises from the unique gravitational interplay between the black hole and the neighboring stars. The Andromeda galaxy boasts yet another fascinating characteristic: an abundance of globular clusters. These clusters consist of densely packed groups of stars that orbit around the galaxy's center, resembling satellites revolving around a planet. Andromeda is believed to host approximately 460 of these dense and ancient clusters, each containing hundreds of thousands to millions of stars that formed around the same period. The extensive presence of globular clusters in Andromeda yields valuable insights into its cosmic history and interactions with smaller galaxies. Over billions of years, it indicates that Andromeda has actively absorbed these smaller galactic companions, a phenomenon termed galactic cannibalism. As smaller galaxies approach within Andromeda's gravitational sphere, formidable forces strip them of their stars and other constituents. The stars from these assimilated galaxies integrate into Andromeda's stellar population, enriching the galaxy's diverse array of stars. This characteristic of accumulating globular clusters and stars from smaller galaxies aligns with the typical behavior observed in spiral galaxies like Andromeda. Spiral galaxies, characterized by their disc-like structure adorned with distinctive spiral arms, offer conducive settings for interactions and mergers with smaller companions. Apart from its other fascinating traits, recent observations and analyses have stirred speculation among astronomers regarding a potential transformation occurring within the Andromeda galaxy. It seems to be in the process of transitioning from a conventional spiral galaxy to a relatively uncommon type known as a ring galaxy. Ring galaxies are captivating and relatively scarce celestial formations distinguished by their circular or elliptical ring-like configurations. These rings comprise bright, youthful and blue stars, while the central area contains comparably less luminous material. Such distinctive attributes set ring galaxies apart amidst the diverse array of galactic structures. Observed optical ring phenomena typically manifest in three main types: nuclear rings, inner rings, and outer rings. Nuclear rings are positioned near a galaxy's center, while inner and outer rings are slightly further out. Ring galaxies primarily fall into two categories: O-type and P-type. O-type ring galaxies exhibit centrally positioned nuclei, featuring smooth and regular ring shapes. Conversely, P-type ring galaxies showcase off-center nuclei, resulting in more irregular ring formations. Ring galaxies are often regarded as rare cosmic treasures, with only approximately 1 in 10,000 galaxies falling into this classification. Astronomers have proposed two primary mechanisms for the formation of ring galaxies. Firstly, they can emerge through the collision of two or more galaxies. Secondly, the passage of a smaller galaxy through the center of a larger one can also instigate the formation of a ring-like structure. Notable examples of ring galaxies believed to have formed from galactic collisions include the Cartwheel Galaxy, galaxy pair AM 2026, 424 and ARP 147. Thus, the dynamics involved are far from simplistic. There are myriad complexities at play. However, what is currently unfolding is even more intriguing. Scientists assert that the Milky Way galaxy and the Andromeda galaxy are on a collision course, destined to merge and give rise to a new supergalaxy. This monumental event has already garnered whimsical nicknames such as Milam or Milkdram, reflecting its widespread recognition. While these monikers may evoke a sense of playfulness, the implications of this merger for humanity could be dire. The merging process has the potential to ignite bursts of star formation in regions where gas clouds collide and compress, thereby birthing new stellar nurseries. These nurseries serve as the cradles for young massive stars suitable for the emerging galaxy. As the galaxies merge, the night sky transforms into a spectacular cosmic display. The collision and subsequent merging will give rise to breathtaking displays of star clusters, shockwaves, and radiant bursts of radiation. As the galaxies merge, the night sky undergoes a metamorphosis, unveiling new constellations and stellar formations. Simply put, the entire celestial landscape will undergo a profound transformation, ushering in a fresh era. However, amidst this grand spectacle, the repercussions are profound as the Andromeda Galaxy and the Milky Way merge. The immense cosmic forces and interactions among stars, gas, and dust will induce significant environmental changes on Earth. These alterations may manifest in various ways within the biosphere, the regions where life thrives. They have the potential to disrupt habitats, trigger shifts in biodiversity, and even spur local extinctions. As the two galaxies draw nearer, their colossal gravitational forces distort each other's shapes, initiating tidal interactions that pull stars, gas, and dust between them. The overlapping of galaxies unleashes chaos and havoc, yet this process unfolds gradually rather than instantaneously. As the galaxies approach, their collision sets off the merger, intertwining stars, gas clouds, and dust clouds from both galaxies. This merging process births new star clusters and structures within the amalgamated galaxy. Amidst the merger, stars undergo significant orbital changes, resulting in a dynamic and tumultuous environment within the newly formed galaxy. Some stars may be ejected from the merged galaxy, while others settle into new, more elliptical orbits. Both galaxies host supermassive black holes at their cores. As they collide, these black holes will eventually merge, creating a larger entity at the center of the newly merged galaxy. This merging process may disrupt the solar system, affecting Earth's climate and weather patterns. Alterations in temperature, precipitation, and weather events could occur globally, reshaping the distribution of vegetation and animal habitats. Changes in solar radiation may impact vital processes for plant and animal life, potentially causing disruptions in ecosystems. While some species may thrive in the altered conditions, others may struggle to adapt. This could lead to increased competition for resources, creating new opportunities for certain species to thrive while posing challenges for others. Regrettably, some animal species may fail to adapt quickly enough to the new conditions, resulting in local extinctions. Disruptions in habitats and climate variations could interfere with migration routes and breeding sites, complicating the search for food and water. With shifting climates and habitats, biodiversity within ecosystems may also undergo transformations. Despite the heartbreaking implications, it's important to note that the collision between the galaxies won't occur immediately. It's projected to commence around 4 billion years from now, with the entire merging process taking an additional 2 billion years to complete. As for humanity, we will have vanished long before this event, and Earth will have already undergone significant transformations. Approximately 5 billion years from now, our Sun is forecasted to evolve into a red giant, expanding and engulfing the inner planets, including Earth. This progression will likely render our solar system uninhabitable well before the merger of the two galaxies occurs. Whether this results in Milum becoming an elliptical galaxy or a large disk galaxy remains uncertain until the merger transpires. However, given the current circumstances, the outcome could swing either way. As the Andromeda galaxy and the Milky Way merge, the cosmic forces and interactions among stars, gas, and dust will mold a new galactic structure distinct from our familiar understanding. Within this amalgamated galaxy, there may exist star systems with planets orbiting within the habitable zone, where conditions might support the existence of liquid water. Liquid water is deemed essential for the development and persistence of life as we recognize it. Nevertheless, the stability of the novel galactic arrangement will be pivotal in determining the potential for life to flourish. The interaction between stars and potential gravitational disturbances could potentially alter planetary orbits and environmental conditions, thereby influencing the evolution and sustainability of life on any potentially habitable planets. While the merger of galaxies may result in heightened cosmic radiation and stellar activity, including rare events such as supernovae and gamma-ray bursts, accurately predicting the occurrence of these events and their impact on planetary environments remains challenging. Should life emerge in the new galaxy, it would likely undergo adaptation to the specific conditions of its environment. The diverse physical and chemical properties of the new galactic region could foster the emergence of a unique form of life, distinct from terrestrial life as we know it. However, contemporary humans would be unable to survive in this novel galactic environment. Thank you for watching. If you enjoyed this video, don't forget to give it a thumbs up and hit the subscribe button below for more content like this. Also, remember to turn on notifications so you never miss an upload. If you have any questions or suggestions for future videos, feel free to leave them in the comments section below. We love hearing from you.